Okay, good morning. This is week 2 in environmental toxicology. Third chat. Catching my breath. I was just up some trees, chopping, chopping and cutting limbs, and I'm exhausted. As the blood sugar returns to my brain and oxygen, does anyone have questions before I launch into a recap of last time and what I wanted to talk about this time? Questions are always good.
I was just going to let you know that on the test schedule, it's a little thing. April 7th is a Thursday and May 3rd is a Tuesday. There's a little like swap thing.
Oh, thanks.
And the link for the Bing in the most recent thing you sent out also doesn't work.
Super. Let me make sure I get that right. Okay. April. Let's see. What did I have? I'll pull that thing up. Where did I put that? Okay. I believe I just sent. Look in La Lima. Actually, that's great. Thanks for putting that out. Let me pull up La Lima and find that and fix it. And there's one or two things I wanted to show you in there. Okay. So let's see. Specifics 2022 specific. Wow. Time flies. Okay, here's our syllabus. Yes, please open. Slide that puppy over. Okay, and the test dates. So April 7 is actually, it's a Thursday. What? So, what was the correction? I'm sorry.
Oh yeah, just that the 7th was a Thursday and the May 3rd is
Oh,
a Tuesday. It's the T and the
great.
R.
Thank you. Fix that. Third is a Tuesday. Super. Thanks so much. Okay. Let me save that puppy. Great. Thank you, Hannah. All right. Okay, so yeah, that's out there. Did anyone have any? That's a great catch. Thanks so much, Hannah. Anybody have any other questions or catches on the syllabus? So those are our nominal test dates. They're not really carved in stone. Like if this were a really big class, then I have to really be inflexible. But they're pretty much dividing up the semester. That'll give us 4 intervals to do 4 midterms, and that way we have the luxury of dropping the lowest. That's always nice. And then I'm going to come back to the list of things that we'll try to wedge in there. I'll have to cobble up some homework assignments. They should be pretty straightforward. I just sent to my other classes a little Word document, and there's a feature in La Lima that my wife uses, I'm going to start using, called assignments. And so rather than using Dropbox, it turns out to be more convenient to use assignments. So these homeworks will be pretty short, probably little calculations that we'll cover in class, assignments. And I'd like to have you guys do some presentations, possibly even 2 of them, pretty short, 5 or 10 minute, maybe a little longer. These are often really surprising. Sometimes when I give them, I think I should just do this all semester because you guys do such good work. Okay, there's that, blah, blah, blah. A lot of the syllabi, I guess, that I do for lower division, they become accretionary, sort of like laws in the United States and regulations. They just build up and never go away. Because in the lower division classes, students spend more time trying to find end runs around the rules rather than learning the content. They try to do their darndest to game the system, and all the questions are about points and grades, and nobody's interested in learning any actual chemistry. And if it's like Pascal's principle, if there's a gas, I think it's Pascal, if there's a gas in a closed container of uneven geometry, the gas, anyone know, will be at equal pressure. In a static system, it'll be at equal pressure at all points. So if there's a leak anywhere, the gas will find it. And this is like syllabi and students in Gen Chem. If there's any loophole, they're going to find it. And over 20 years, it's been interesting, the ones they've found. So I sometimes adopt a very stern tone, parental tone that I don't like myself. I don't have children. I'm looking for children, and I love having upper division and graduate students. Yay. That's all I used to teach at Manoa. So, all right, jumping back here. So that's that. If you have any questions on that, thanks very much, Ms. Hartman, for that great catch there. Let's see, get back to this study guide. So I passed this thing out. Come on, slide up. Slide. There we go. Last time. Oh, no, not this one. Okay, this other one. Oh, yeah. Okay. Musical sliding window panes. All right. So this is what I passed out last time. And I believe I discussed this briefly last time. I had in mind to do this first set. As I mentioned earlier, we're going to do the course like top down, take a little tiny corner of a big, huge terrain and take a look at that microcosm. It could be a set of scientific papers or a particular event or a real world phenomenon. And we'll sort of drill into that from the top. And then we'll go back to more traditional as bottom up, fundamental principles that govern these things, which a lot of times is all you ever get in undergraduate level, and I feel that's a mistake. So I'd initially picked set one, which is inhalation toxicology, one of my areas. But I did have these things, look for these basic things. What can we generalize, abstract from the abstracts, generalized takeaway from this little glimpse in this little corner of the huge area of ETOX. So noteworthy of strengths or weaknesses of a study, or in this case for the oxygen catastrophe, there was one or two papers and then some YouTube videos and stuff. So strengths and weaknesses, any assumptions, implicit or explicit? Okay. Do you have any concerns about their methods, their data collection, or their interpretation inclusion? Think critically. Don't just think that because they're publishing in a top journal that it's all been properly vetted. I knew someone who was publishing in Science and Nature, like the two top journals, and a bunch of pH data that had to do with something in the ocean, and didn't know that you had to calibrate a pH meter. And it was stunning. Okay, so yeah, so be suspicious. You guys are, training to be scientists, so that's what you do. You're suspicious and question stuff. So we're taking this really close-up view, nearsighted view of environmental tox, and so each time we dive into the deep end in one of these top-down things, we will hopefully always discover our personal ignorance, and that's not a personal failing. That's just being honest. Everyone's ignorant, just of different areas. And honestly, in any subspecialty, if you take a long nap, you're probably out of date. So knowledge is growing exponentially. Humanity is phenomenally ignorant of a lot of things. It was within the lifetime of most of you that they figured out that only about 5% of the known universe that we know about so far is made of these atom stuff, protons, neutrons, and electrons, which we used to think made up everything. So there's that, as Jesse says. Some of the questions that come up for you as you're going through these things and any general lessons. Okay, so it's possible to get lost in the weeds, and I mentioned that because I tossed at you a wiki page on the Oxygen Catastrophe or Great Oxygen Event, GOE, and there are a lot of weeds on the wiki page. I'd initially tossed a link that was very much at the bottom of that page. I revised that up to the top, but there's a lot of weeds in the middle. So I was just reminding folks not to get lost in those weeds, but that sometimes it's in the weeds that you find things. You know, down in the weeds, you find some of the most questionable things. Wait a minute. He assumed what? Everything's at equilibrium? Okay, so we're skipping set one, remember, and we'll come back to that. Great oxygen catastrophe, and then I sent you this other document. We'll open that up soon. Another example of top-down, real world. And again, our aims are gain a sense of the problems encompassed by environmental toxicology. Look critically, and critique a tiny subset of these investigative approaches. And hopefully this motivates us to better understand these fundamentals that I will drill and harp and come back to and train you up so that you see something out in the wild and you can spot some fundamentals and ask good fundamental questions. Okay, where fundamentals are bottom up, like how do chemicals move in the world? What happens to them? How are organisms exposed? What are the effects of the organism, etc.? Okay. So, there are a lot of fundamentals. We'll drill down a bit into some of them. This course, I could teach any one of the sub topics. I could teach a whole semester. Geez. So we want to be well versed in the fundamentals so we can ask good research questions. So I know a number of you, all the grad students are doing research, yeah? Geez, we wish we had more time in these courses. I eventually want to do a little round robin of intros and hear what people's backgrounds and interests are. There's just so much material to cover and so little time. But a lot of times you'll see work in the literature that there's not a very well-framed research question, and people just start chasing smoke, so to speak, as I did myself in VOG research, quite literally chasing VOG. Or if you have a hammer, you're supposed to ask me on this, what looking for nails. So that's something researchers do. Maybe some of you know that. Maybe somebody has a particular instrument, like I don't know, maybe. Like we have some folks here that do stable isotope research, and there's a great instrument for that, a mass spectrometer that looks at stable isotopes. So, you know, or someone might have a GCMS or an HPLC or atomic absorption or XRF or something, or ICP for metals, and they have this hammer and they go around looking for nails. You know, I got this tool, what can I measure with it? So tool-driven research occurs in the world. Okay. Useful environmental sampling. So where are you going to sample? What are you going to measure? Not just chemical measurements, but there are a lot of environmental conditions, you know, temperature, pressure. Are you, you know, sampling in a mobile medium like a river, the ocean, soil, rain? You know, what are the conditions? Is it freezing? Is it flooding? A whole bunch of things, atmospheric, there's huge dynamic environmental measurements, temperature, pressure, humidity, all kinds of stuff. And in that milieu, in that stage of the environment, whatever parcel of the environment you're looking at, what chemical measurements might you make? And again, this should all be driven by the research question selected. Keep that in mind when you're reading these papers. And useful analysis of those measurements. Once you get the measurements, you have to do some kind of statistical analysis and then make some interpretations that make sense and make some conclusions based on those interpretations of those measurements and so forth. So coming back to these basics again and again and again. Sources, where did environmental toxicology? Well, she poisoned me, he poisoned me, you know, it was a poisonous look. I mean, where did the poisons come from? How did they get from point A to B? What pathways? How did they, which particular pathways? And there might, so we talk about modes of transport, which I introduced last time, but there might be several modes of transport involved, as we'll see. And what are the organisms involved? How are they exposed? How are their doses? We won't necessarily dive into this right away, but later this will become very important for us. An organism's dose, it's not the same as their exposure. Exposure is outside the organism, dose is inside. And once we get some toxicant into an organism, what are you going to measure? There's all kinds of stuff. I think I mentioned the old school toxicology was they kill a bunch of rats, they count the feet pointing up in the air and divide by 4. So that's pretty crude toxicology. Or they might do what's called gross necropsy, where they you cut open the animal and you see, is the liver the normal color, so that the normal size, or is it extra, it can be twice the normal size. You weigh them, you look at their color and their texture, you make notes. Okay, can there be toxic responses that we didn't measure? Of course, always. Yeah, so questions governing behavior of matter are primary concerns. Okay, right. And then more complicated compound questions that hopefully you found some amusement. Do browse through these things. Okay, getting back to our basics, key study points for the first test. So there's this list here, and I'll pull up another page where I have the larger list. And we have these things in here. This is the bottom-up approach, and that we want to consider when we're looking at the great oxygen catastrophe. What are the compartments involved? How do chemicals move around? Points of view I haven't really described that much yet, but briefly it's listed here. Systems point of view, we'll get into the systems theory 101 or 001 more likely. A molecular point of view, 2 molecules walked into a bar. See, I mentioned last time, one might have loose electrons, and in a rough neighborhood, they might get stolen. An organism point of view, I thought it was good to eat. It was a good idea. It seemed like a good idea at the time. Where do things come from? Sources and sinks. This will be important when we review oxygen, related rates, mass flux, and flavors of toxicology. It's listed somewhere else. So those are some study points. And then these are some of our tools I discussed briefly last time. We'll dive into these more. Feel free to do some of your own work. And on that note, so just briefly, the octanol water coefficient, Henry's law, and I want us to think of these as partition coefficients, which KOW definitely is, between octanol and water, where octanol is a stand-in or surrogate for lipids or biota. And Henry's law, partitioning between air and water. It's generally taught differently, though. In Gen Chem, it's taught us the more pressure you push a gas over water, the more it'll dissolve in the water. That's how it's usually taught. We're thinking of it as partition coefficient. Pourbaix diagrams, hydrogen ion, pH, activity, which we'll come back to, and electron availability, redox status of the matrix, whether it's air, water. Usually there's some aqueous fraction, some watery bits. Well, just because some watery taught through a soda cheese, no basis for an autocracy. And some other tools. Okay, alrighty then. So here was the quick sources of info on the great oxygen catastrophe. I do hope you all did your homework and jumped into this. There's a lot of swimming, but the first link I gave, it's okay if you looked at that. It was the tail end of this. This is really long and chewy. I didn't expect you to read and memorize the whole thing. This is a little shorter. This is an interesting variation of the Gaia hypothesis, and some actual science lit. These YouTubes, I do hope you all looked at least several of them. I like GeoGirl quite a bit, the way she presented things. Those are pretty good. I like to watch those and discuss them in class. What happens with that, though, we may get to that, but what happens with that is that I might run afoul of copyright things when I post this. So we might come back to that at the end and have a peek at that. Maybe I'll pause the recording and I'll start it again so that in case it is copyright flagged, we don't lose everything that we've already done. And I don't have to spend hours and hours trying to edit the thing. It's pretty easy to edit a chop off, but it's a real pain to edit out a window. Okay, so did want to pull up one more thing. Oh, these bars here. Does anyone have any questions or comments? Did anyone find this fascinating? How many folks? Show of hands. I wish I had a bigger screen. I need to get another screen where I can see all you guys. Where are you guys? Like Robin Williams in Good Morning Vietnam. I can't see you guys. Show of hands. How many? Just chime in. How many had heard of this? All right. Is it just new to anyone?
Oh, it is. Yeah, this is brand new to me.
Quite surprising, yeah? Like pretty catastrophic. They don't, my wife and I like to call it the Great Catastrophe, but most people call it the GOE, Great Oxygen Event. For heaven's sakes, it was a sea change or air change anyway. Okay, let's see. Right, oh, this one. Okay, that's for another class. Sorry, drag that down. Okay, the Blaustein paper. So this was, I believe it's this link here. Let me just pop that up and make sure. Come on. Yeah, Blaustein. Wo ist Richard? Hierher. Kommen essen. Okay, come on, shift that back. Get that down, and here we go. So here's the Blaustein paper. So before diving into this, what were the basic, anyone want to launch in, and what was sort of the basic story? Anyone want to pretend I'm a bright 9-year-old? It's not difficult, except just to dye my hair, shave my beard. Tell me the story. What happened here? Anybody?
Well, what I could start off with was that the premise was that the NSF, the National Science Foundation, they conducted an investigation on the Great Oxygen Event for 5 years, which composed of 21 researchers. And over that time, they had it was a huge collaboration of people in different fields, where some of them were looking at like volcanism, a lot of them around the Earth's plate tectonics, geology related topics. But there were 3 prongs of the research scope that they wanted to look at. And one of them was where they looked at the biochemistry of the oxygen photosynthesis and how that all evolved to be energy drivers for the cyanobacteria, which what we learned were responsible for that event. And then they also wanted to ID when oxygen photosynthesis first occurred. And then the last would be they looked at a lot of the diverse geological and biological factors that sprung all this into action for the Great Oxygen Event tipping point.
Okay, right. That's great. That's a nice summation of that study. Taking a sort of a big step back and several steps down in grade level for my sake and the studio audience at home. Targeting it for a 9-year-old or 6th grade level or something, which is what they say most TV is targeted for. Oh. Suits me. My blood sugar's still catching up.
Oh yeah. Let me.
What happened?
Yeah.
That a child would understand. Anybody, somebody else.
Yeah.
So another person. And it's great if you guys feel like turning on your cameras. So I don't know, it's up to you, but make it a little more interactive. But that was great, Blake. Thanks. That was a very nice summation of the NSF study. That was well done.
It was. Thank you.
Broader brushstrokes. Anybody? What happened?
I'll kind of throw it out there, but from how I was like reading it, it's basically a lot of people think that oxygen actually, it did bring a lot of organisms into this, able to live on the Earth, but not a lot of people understand that there was actually a lot of organisms that were before the Great Oxidation Event, right. And not a lot of people realize that actually oxygen is toxic to most to a lot of animals in the world. And I think it kind of was a new like perspective, like if it wasn't for the cyanobacteria, you know, would there be other animals on the earth or multicellular organisms? And kind of looking at it from a different perspective, you know, thinking that oxygen actually allows things to be alive. It actually killed a lot of things too.
Well put, sir. Nice. I like it. Nice synopsis. Somebody else chime in. What else?
Yeah, I can add to that. So basically, many billions of years ago, when the Earth was still fairly young, most of the animals and plants, organisms on the planet were what's called anaerobic. So they did not use oxygen, and that's what Matt was getting at. Oxygen was toxic to them in high concentrations. And then this one particular type of organism called cyanobacteria developed the ability to photosynthesize and basically use sunlight and water and CO2 to produce sugars, and then its waste product was oxygen. Many millions of years go by where they're producing this oxygen. There's lots and lots of cyanobacteria growing. And then eventually this buildup, well, actually before the buildup happened, there was a lot of geological sinks, it sounded like. So like all of the iron on the planet rusted, oxidized. And so it took many millions of years for the buildup to happen, because there was all these sinks that had to happen first that were absorbing the oxygen basically produced by the cyanobacteria.
Great catch, Jessica.
And then eventually that did happen, and there was a little bump in oxygen. I think it was like 1% of current levels or something. I can't remember the exact number, but little bump up, and that caused, I think, that huge extinction event of all these anaerobic animals and plants that couldn't survive in an oxygen-rich environment. And then there was another bump after that, once the cyanobacteria kind of came back and were able to survive in their own waste, essentially. And then that big bump that got us up to about where we're at today, 21%, came right before the Cambrian explosion, which is what we know when all life exploded, and we had this huge diversification of multicellular organisms.
Nice. Strong work. Anybody have any to add to that, or questions, comments? That was beautifully done, Jessica. Nice. Nice story. Okay, let's take a look at this paper. Yeah, so there was the world, and wow, life evolved somehow, and that's a really interesting question. A friend of mine, Dr. Heather Kaluna, she's an astronomer, teaches astrobiology, and I sometimes guest lecture for her class. And the question is, how might life take hold anywhere? It's a really intriguing question. You probably many of you may have heard of this Urey Miller experiment, Stanley and them. Professor and a grad student thought the old universe, Earth's atmosphere used to be, they guessed methane, ammonia, water vapor, and they put it in a flask, something like that, and maybe a little pinch of dirt, and they had electric sparks to simulate lightning and give energy to get over the energy hump, because they didn't assume any enzymes, prebiotic, so no enzymes, right? So you got to drive the reactions. And they cooked it for a while, and they wound up with a whole bunch of amino acids, which they used to think were just made by biota only. In fact, the term organic chemistry was, they used to believe that bunch of these molecules were made exclusively by life, organisms. That's why they called it the chemistry of organisms, organic chemistry. And then to find out that things like urea and stuff they could make without life. And so the Urey Miller experiment found complicated and similar experiments. They found amino acids, nucleic acids and stuff, all with abiotic processes. Remarkable. And then somehow life got kick-started, but it was anaerobic. And has anyone had microbiology? I gotta get to read everyone's who's filled out there. Great, yeah, so there's obligate anaerobes that if you give them as Jessica says, a whiff of oxygen, as one of the authors in the paper said, a whiff of oxygen might kill the obligate anaerobe. And it's really toxic. It's a really reactive gas. Most of the Earth's crust are oxides and silicate oxides and stuff. And I used to work in semiconductor safety industry, and the guys that make the chips in your computers and phones, and they use the metalloids like silicon, arsenic, germanium, boron, and they use these semi-metals or semiconductors, and they dope silicon with them. That changes their band gap, blah, blah, blah. I can bore you with a bunch of PChem and double E, but they start with those semi-metals like silicon and arsenic as hydrides, silane siloxane. I'm sorry, no, not silane. Silane, arsine, phosphorus they have phosphine, and these hydrides are super reactive. So if they escape, if they have a leak, and these are things that might have existed in the Earth's early atmosphere in a highly, highly reductive environment when the volcanoes are spewing out gobs of these highly reduced gases. And if these things were around when oxygen is there, now if they leak, and then 21% oxygen is quite a bit, they're pyrophoric. Does anyone know that term for 2 cents and the rubber duck? All right, sorry, Groucho's not here, but pyrophoric is a material that spontaneously ignites, busts into flame on contact with air. Lots of fun. Every 13-year-old boy's dream. So that's what happens in the semiconductor fab plants, and we try to prevent that. I was part of the Safety Association. Anyway, TMI, but the early Earth's atmosphere and how it might have changed, it's a really intriguing thing. And as Blake mentioned, NSF, they cobbled together a really great, bright, motivated group of boys and girls that attacked the problem from, what was it, Blake, four different angles or something? Good.
Oh, well, there's multitudes. They had scientists where, for example, they looked at plate tectonics,
Right.
parts of the Earth, the volcanic activity, the interior part of the Earth's geochemistry. Then they had their biologists that looked at the cyanobacteria activity. So it's just, what was interesting was that one of the researchers, I think, in a passage said that the environment is, the organism's biology is just as influential in the environment as it is vice versa.
Right. That was a mind blower for me. That's a good catch, sir. Yeah. It's a two-way street. Blake's absolutely right, folks. The minerals and biota affect each other in much greater degree than I thought. I would have thought it was a one-way street. Minerals affect biota, like lichens. You probably all have heard of an algae and a fungus. They have a mutualistic symbiosis, and they sit on rocks, for instance, and the fungi will secrete acids, rendering the minerals available, solubilizing the minerals, making them bioavailable to the algae, which need them. The algae photosynthesize and feed the fungi, and so they get on quite well with that mutual symbiosis. But that biota chewing up the minerals and actually participating in mineral formation and influencing element cycles, it's much more profound than I had known. That's a good observation. Thanks, Blake. So
Absolutely.
a long time ago, can't do the regular Kipling, sit back by the fire, best beloved. So there was a bunch of the Great Oxygen Event. Note that there was a lag. Can you guys see this on the screen? On screen, Captain.
Yes.
The notes don't get any bigger, but there was come on now. There was a pause or a lag, as Jessica mentioned. The O2 production came out from the cyanobacteria, and between when they started pumping it out, well, they pumped it where? So what was the source? Source is transport sinks. We'll come back to this again in a simple diagram with systems point of view. What was the source of O2? The cyanobacteria, I think we all agree. Where was it? Generally speaking, shallow seas, that kind of thing. Where did it go? The oxygen. I think a lot of them might have been aquatic organisms, so initially maybe into the water, and then where did it go?
Into the atmosphere.
Absolutely, into the atmosphere. There's a term, it's actually a physical chemistry term. You could jot it down and look it up later. Fugacity, write it down. It'll be one of our vocabulary words for the next test, fugacity, along with activity, chemical activity. Fugacity is the ability to flee, or its ability to get out of Dodge. It's mobility. So oxygen has pretty good fugacity in water. It can partition out of water into air, as Hannah just noticed, and it can also partition into the sediments or something, react with the minerals, as Blake was mentioning. It can react with just about anything, and it can react with the biota itself, as Jessica was mentioning early on. They were killing each other themselves. So where does it come from? Where does it go? How does it move around? But there was a lag. And we got to wonder about that. And Jessica observed there was a sink, a geological sink. So that's, again, biota making oxygen and oxygen getting gobbled up by the iron and stuff. And there were 2 steps. There is a step from no to low atmospheric oxygen, and Jessica did mention this, and then the big bump, the high leap. And so we'll think about that. And it led to the Cambrian explosion. Okay, stromatolites. Come on, go away. Go away, you silly nut.
Essentially, though, the oxygen that the cyanobacteria are producing, at some point beyond millions of years later, was actually working to outcompete the sinks that the iron was able to store the oxygen in. So that's how we had that expanse of the oxygen levels. What I was reading.
Bingo. Very good. I love this. That's a good observation, Blake. I love this when scientists are frank, but we still don't really understand. Tons of research, overall understanding. So what's that ellipsis there? How can I? Oh, I see. It's offering an opportunity for reply. Okay. All right. Managing this thing. And here's the tree. I'm going to tell you a story. The 3 little pigs, they went huff, they puff, and the NSF blowed his puppy down. The 3 prongs that Blake was mentioning of the, I thought I had a comment there. I must have been speechless. Blake covered that nicely. Okay, a second and very hearty line of research. When oxygenic photosynthesis first occurred, so what was the foist? Come on, hold still. First looks at the biochemistry. So this is interesting, and one of the YouTubes I popped up dived into that nicely and showed that actually it wasn't just the anaerobic metabolism that we're familiar with making ethanol or lactic acid, which garners you a couple of ATP, but actually it could probably crank through citric acid and the electron transport chain, but instead of oxygen. Does anyone remember what was the terminal electron acceptor at the end of the electron transport system? Instead of oxygen, before oxygen was available, what was there? That allowed that little ATPase lollipop enzyme to spin around with the proton gradient from the outer the membrane in the mitochondria and the cristae. It was sulfur. Sulfur was the terminal oxygen electron acceptor. And instead of making, sulfur is directly below oxygen in the periodic table. And so what happens to oxygen with photosynthesis is the oxygen as a terminal electron receptor. Remember oil rig or Leo the lion went grr? So this is a mnemonic you all should know. Oxidation is loss, reduction is gain, oil rig. Okay, we'll come back to that. Third line of investigation, diverse geological, biological factors produce a tipping point, which both Blake and Jessica mentioned, is that eventually things came up, enough oxygen was there to saturate the geological sinks. And then there was a tipping point where it started to build up in the air. And this is a two-way street, again, biology and geology. Okay, this was striking to me. Blankenship noticed that the 7 of the, I imagine these are extant or still existing bacterial groups, 7 photosynthetic bacteria, my heavens. So they say blue green algae, but I guess bacteria predate that, or maybe they called them algae because, hey, you're in the club. The biologists call it let's see, heterotrophs or autotrophs. Troph, to eat or consume, I guess. Hey, we're all heterotrophs. We eat others, vegetarian or not. You can still hear those little corn embryos squeal. We eat others. The plants eat, they don't really eat themselves. They eat sunlight. What did they eat before that? Anyone? What was the energy? Sorry?
Chemicals.
Yeah, that's pretty good. That's never hard to go wrong with that, Mr. Dye. Can you narrow it down for us, sir? Just a wee bit, a little dram smaller than.
I would say sulfur.
Ooh, sulfur, probably. I'll bet. Yeah, that could be. Sulfur has looser, fluffier electrons, but it's a non-metal and it's right below oxygen, so its electrons are more available for ripping off than oxygen's. But what else might be a source of electrons you could rip off to oxidize to gain energy?
Glucose.
Glucose. Yeah, good. I don't think there was much around then. There might have been, but yeah, there probably was. But they're making it for themselves. But that'd be like the Apaches robbing the Navajo and the Hopi for their corn. One of the early sources was reduced sulfur, like hydrogen sulfide, and another would be metals. Metals have loose electrons. Of course, I'm an excellent driver. First, anoxic photosynthesis. Oh, here we go. Rely on iron, hydrogen, or other electron sources. So before there was sunlight to eat, they were eating chemicals. So this kind of supports the point of view, as Blake and Samantha had both mentioned, that things really got cooking. And Matt also mentioned this, is that things really got exciting when a lot of oxygen was available. And I think Matt was the first to say that we got a multicellular life. These resources here are you're going to run out of them at some point, a finite resource. And if life exponentiates like life likes to do, they're going to run out, what they can reach anyway, until tectonic shifts more. But on Earth, hey, we get choke water, So from a systems point of view, from an organism's point of view, looking out, this viewing an organism or biota as a system, looking at outside to its sources of electrons, it can only mine so much of these things. But once there's a lot of water on the Earth, right? So from a systems point of view, they would see that as an infinite source. Okay, we're going to go to simple diagrams real soon here. But co-evolution, ability to make oxygen and protect yourself. So yeah, this was mentioned by a couple of you, and Jessica in particular mentioned that they were killing themselves, They had to be able to survive their own poo, their own waste. So this is one of the first major steps in toxicology, toxicity, is that they were able to deal with that oxygen. And does anyone know how we deal with it? Some of the enzymes or antioxidants that our bodies make, or vitamins? Vitamins, if you're British. So within our bodies, so vitamins, we've got vitamin C and E in particular are very good antioxidants, along with the carotenoids. And in the body, we've got our own called glutathione, it's reduced sulfur. And enzymes, we've got catalase that breaks up hydrogen peroxide stuff. So whiffs, I love this, whiffs of oxygen. Okay, traces, did I have some comment there? Come on, I see it trying to pop up. It's like a little ghost of a comment. Nothing there. Oh, here it is. Come on. Oh, there it is. Evidence suggestive of dynamic interaction of a two or really three-way street. So vis-a-vis what we were talking about the last time, we wound up with, I talked about compartments, basic compartments, and I said that most environmental chemistry books that you can pick up, and there are dozens of them, trust me, I shopped a long time, they divide the world typically into three compartments: earth, water, and air. And I contend that biota is a very major and significant compartment from our point of view. So how many compartment systems? And so it's a 2 or 3 way. This is evidence of interaction. Oops, okay. On the screen, Captain. This traces of stuff going back that far. All right, see if I have any other marginal comments. Marginal in every source of the word. Yes. Okay, sources, sinks, and related rates. Okay, so there was oxygen production, but it was simply not sufficient to oxidize all the things in the environment, as has been mentioned. The iron, the banded iron formations, BIF. So there were sources of oxygen and sinks, and there were related rates. We'll come back to that. My mouth's too dry to say that right. So isotope ratios and sulfur fractionation. And when we got enough oxygen in the atmosphere, we got this ozone layer, and then the high energy events that if you're at a high enough energy level, you can do lots of atomic molecular dances. You can do a lot of chemistry that you cannot do at a more restrictive lower energy level. And so there was mass independent and mass dependent sulfur isotope fractionation. And once ozone blocked out the UV, that strong energy source wasn't available as much as it used to be before the ozone to drive sulfur isotopic chemistry. And once the ozone block got there, once the Earth got sunscreen, well, that restricted the sulfur isotope partition or fractionation that they're talking about. So he's saying it just turned off. Well, that's not strictly speaking accurate. It switched from, and I'm a little unclear on people's usage of the independent and mass independent and mass dependent fractionation. When you look them up on Wiki, sometimes definitions in Wiki seem to be a little bit self-contradictory. I maybe need to dive into that a little more, but so the sulfur isotopes measurements established be the minimum. So there had to be a little oxygen to create that ozone, and it didn't need to be much, like 0.01%. So strikingly little tripped the switch on the sulfur fractionation. So that's one of the chemical signatures that oxygen showed up at that low level, and then a deep drop in oxygen, and yeah. So that was, might have been the event at the bottom of the wiki page.
I have a quick question.
Yep.
The development of ozone, would that have slowed down photosynthesis? Like, did that affect the way that, like cyanobacteria produced O2 as well?
I would expect that it would. That's a strong, very strong research question, Mr. Dye, and I suggest you write the NSF a grant proposal as soon as you get your PhD. And and that's a really interesting question. Sunlight has an ultraviolet component, and if you remember Gen Chem, E equals H nu, the frequency with ultraviolet's the highest frequency. Energy goes up linearly with frequency times Planck's constant. And so that has a lot more energy available to support photosynthesis. And once that is screened out, I would imagine there might have been a shift. That's an excellent question. I don't know, and I'd be surprised if anyone knows. That might be a superb, what is called in science, original question. So that's, by the way, a major attaboy. High fives, Mr. Dye. Original question is a strong bit of work. So good job. I don't know. Volcanoes may have shifted locations, shifty. Oh, that one just went off, the Hungatonga. Yeah, you guys read about that, yeah? That was exciting. Poor guys, though, wow. Implications are dramatic. Plate tectonics. Okay. Dynamic plate tectonics at work. Complex change. So as I think Matt might have mentioned early on, stuff going on, or maybe it was Blake, deep within the Earth. There's geochemistry going on below the surface, and tectonic stuff is bringing things up to the surface. So systems within systems. So we'll get back to that. Supported by cyanobacteria and help bury carbon detritus. So part of the larger, longer term carbon cycle involves geology, tectonic plates subducting, going deep, go deep, go deep. I'm going to throw one long pass. So it goes deep into the earth and it comes out from volcanoes often as carbon dioxide. Okay. No such thing as water-rock interaction. It's water-rock biofilm interaction. Well, when was this not true? There's no such thing. So two systems interlinked and interacting is like simplistic, ideal, equilibrium kind of thing we learn about in school. And many of the laws we look at or trained in are two-system laws or two basin equilibrium, two condition equilibria, more than two systems. This is a three-part system, water, rock, and biota. But when was that not true? He says there's no such thing. There absolutely was. He said there's the word is there. Was it Bill Clinton? Depends what does is mean? Never mind. Hopefully you guys missed a lot of the OJ drama and Bill Clinton, Monica. It was just like the country going bonkers over. There were actual real global problems, but nobody could be bothered with those because we had to be busy. Anyway. Well, there wouldn't have been a biofilm present before life. That's just my thinking there. Okay. All right. Enough on that. All righty. So, new screen. Okay, I did just want to point out, and what I'm considering doing, so I would like you all to, at some point later on in the semester, probably a little past the halfway point, I would like everyone to do a little talk on some topic of environmental chemistry that is of interest to you. But before that, I hope you have availed yourselves of the book. This is our book, Stanley Manahan. I've spoken with Dr. Manahan, he's an amazing fellow. I think this is really one of the best, by far, environmental chemistry books you can find out there. And just browsing down the titles here, you know, what is the environmental science and what is environment? A lot of basic stuff and compartments, air, water, hydrospheres, it's atmosphere, some say geosphere, biosphere. So we've got the compartments, and now they talk about the anthrosphere. So what compartment is missing? Remember last time I suggested that my opinion was that there were, air, water, they got air twice there, huh? Oh, I see. Water, air, earth, life, and I said at least one more.
Oh, if I may interject, space.
Space, the final frontier. To boldly go where no one has gone. Yeah, space. And the late bombardment is what brought a lot of heavy metals to the surface. They didn't sink into the core. And so that's why we have such exotic chemistry on the surface up here, and possibly life maybe have been brought. Okay, so these are some pretty fundamental things, energy. So what I'm suggesting here, just fate and transport, some of our fundamental things. Reactivity, chemicals react as they move through the world, especially with oxygen running around. Speciation, chemicals can change species. We'll look at that. Mass balance equation or expressions. We'll take a little bit look at that. Pollutants. So this goes on, and I again encourage you to take a dive through this and pick one of these topics that you find interesting. Maybe not automation and robotics, but something that is more apropos or directly applicable to environmental chemistry, and pick one of these and maybe to give a talk on. And this goes on and on and on. This is a very thorough and exhaustive book, and it's an impossible topic to cover, but my heavens, Stanley, Dr. Manahan really does a really good job covering a lot of ground and digging in And here, remember I mentioned the POV diagrams, PE, pH. So read all about it. Hopefully folks have wikied those already, but that's, this is, some people call it EH. They'll have like E and an H, pH or PE, or it might be called the POURBAIX, POV diagrams. So we'll take a look. So I'll be talking on that. So pick something else. Humates and fulvates. So there's just a lot of juicy stuff in here. Phase interactions, solubility. KSP for everyone that's had Gen Chem. And it just goes on with a whole bunch of stuff in here. There's subtopics everywhere. And so pick something in there and that you want to give a little talk and bounce it off me, please. But do take a wander through this. And, as you progress in graduate studies and professional schools and in your careers, you might want a book like this on your shelf, because who remembers everything? If I, dive into something and find detail, and you all took equilibrium when you had Gen Chem, and, nobody told you there's going to be a short quiz in 40 years, but there could be. So being able to go back to these books, and this is a good one to have on your shelf. When I was the state toxicologist, essentially for the Hawaii Department of Health, back before it was an official position, but that's what I was, and the only PhD toxicologist in the whole entire Department of Health until Barbara Brooks came back. And then I got a job teaching at Manoa. Barbara was still there. Anyway.
So would you like us to go over a whole chapter or just a section of a chapter?
Yeah, just a little, like maybe one of these dot, or even these sub dots, but not a whole chapter. Absolutely not. No, you got to do this in 5 or 10 minutes, 15 tops. We got 16 at last count in the class, so it has to be short. So probably maybe even one of these sub topics. Good question. Okay, so those are there. So as we're going through and we talk about things like I have mentioned in materials I've already passed your way, and I realize that there's a plethora of material. There's chock stuff in the resources. There are a lot of things, but some of the things I have sent to you as active, look at this. I dragged it to your attention. So please do look at the things I wave aggressively under your nose. But this is Agency of Toxic Substances and Disease Registry, toxicological profiles. I have monographs on things that are always out of date by the time they're published, but there are a lot of things. And this just goes on and on. So this is something I did an awful lot of: trace gas analysis, atmospheric monitoring. There's a lot of stuff about that. So that's why my physics friends would tease me, here comes the airhead again, is doing trace gas analysis. But my buddies I worked in the Institute for Atmospheric Physics in Tucson for years, and those boys and girls are amazing. Like astronomers, you got to be 7 feet tall to walk in and say, hi, I want to do physics with you guys. They often take 10 years to finish their PhDs. Terrorism. I worked on an anti-terror group with Army, Navy, Coasties, Civil Defense for several years, both through the Department of Health and as a professor of public health at Manoa. It was a really interesting group. We did a lot of interesting work. Okay, so, right. Systems. Any questions, comments? That's an example of top-down, the Great Oxygen Event.
The book that you were just going through, what edition is that? Is that
this is the 8th. What are they up to
okay.
now? Does anyone know?
I don't know. The one you posted is the 7th edition,
Okay.
but it doesn't have it's not quite it has the same stuff.
Okay. Well, you might be able to find this one on there. Okay, so, you do remember from last time we talked about our basic 5 compartments hour for purposes of our class. So you might see me using shorthand notation. I might say FOP for our purposes or something, hour. So this is for this course. This is just my point of view. This is generally accepted. Most books of this nature cover this. I contend that here's where a lot of the action is, and this is actually quite important. And like I said, about 70,000 tons per year, still coming down. Already. Okay, and what were the four modes of transport? You can huff and puff and blow the house down, blow the house down. Now, on the test, you will be asked to list four modes of transport. These are them. And give 3-word definitions, which I've done for you last time. These are those. Simple, yeah? And an example. Got it? You can plan, you can expect to see that on the first test, just so it's not a surprise. Advection. So examples, wind currents. If you say wind is okay, if you say currents, please say something more than that, like river currents, ocean currents, something like that. Be a little more, don't just say currents. I'd think electric currents, or I might think those nice little things you make jam of. Just add a little more juice than a single word, please, please, please. Okay. Diffusion, as my friend from Niger would say, this deep, rich voice, French-speaking Afrikaan. Diffusion. He sprayed his little Quonset hut with a pesticide and wanted me to go in and have tea. And I said, no, thanks, Wabu. The pesticide said, no, it will leave by diffusion. It will be gone and it will be safe and we can breathe. Say, yeah, but that takes a day or two. So let's just have tea outside. Random, molecular, motion. Now, of course, we could substitute for molecular, could be ionic or atomic, but particle. All right, biovectors, life moves stuff. I mentioned the salmon, or humans put stuff on ships. We are biota, and ships, we move a lot of stuff. If you've seen mining activities, a lot of stuff moves. Ballistics. So what in the national news, what environmental chemicals were just covered in the national news in the last couple of days moving by ballistics? It was big. You could see it from outer space. It made a big poof from the satellite.
Volcanic. Yeah,
Volcanic, thank
the
you.
volcano.
Objection, Your Honor, leading the witness. Yeah, the volcano went poof. And Pierre's mustache went poof. The volcano, it lobbed up to like 40,000 feet. And that's above the troposphere, where it's starting to get it. Well, it's in the upper region of what they call geostrophic winds, or the jet stream, where you can get a lot of lateral transport. I was looking for examples of that and I haven't found. We'll talk about plumes later. You're responsible for these. Okay. So systems, we have 3 from our class, are going to have 3 POVs for our class. We'll have a systems point of view. We'll dive into that. We'll have a molecular point of view. Now, this could be any chemical species. How do you spell a molecule? Molecular point of view. And we'll have an organismal, or it could be population. So these are all points of views that we will dive into and view the world from these point of view toolkits. Okay, so systems theory. I hope you are taking it upon yourself to dive in and educate yourself a little. As soon as you hear when that flag went down last week, and I mentioned this, the good students will have looked that puppy up, at least wikied it, or something. I mean, just something about it. Okay, systems point of view. So systems 1010101. There's our system. It's whatever you define it. I think I might have mentioned last time, that could be a planet there, it could be a cell. And some people call it box model, and instead of a ball, they draw a box. I don't care. We can have fun with polygons, just like, that's great. The idea is the same. And you got stuff that can come in, and you got stuff that can go out, as denoted by the arrow. And we can even label those puppies in and out. And we can have, for instance, mass. We can have chemicals. So chemicals or mass in the form of, say, some chemical or other, like, say, oxygen, for example, can go into a system and then it can come out. And it might come out by different ways, and it might come in by different ways. So the ways that it comes into the system, collectively, the places. So this is our system here under consideration. Now, the things where the stuff of interest, and we select what's of interest, like for instance, with the GOE, the Great Oxygen Event, the chemical of interest was dioxygen, molecular oxygen. By the way, ozone is also molecular oxygen, but it's super toxic. It'll kill you if you breathe much. That's a molecule, that's O3. Those are not the droids we're looking for. Thank you, Obi-Wan. These are what we call, from a systems point of view, sources. Not too surprisingly, because they come into the system from these sources. So what was in the GOE, Great Oxygen Event, what was the source of oxygen?
The cyanobacteria waste product.
What?
Oh, I said cyanobacteria is waste product.
Yes, cyanobacteria, way before Walmart. Okay, and then how the oxygen went out? So these days, let's look at present day. Let's say that oxygen comes in and the oxygen goes out. And generally, what are the sources? Let's just scribble this down to one for oxygen coming in. Right now, the sources for the production of oxygen on planet Earth, I'm going to go with photosyn. Is it a sin? I don't know. My father was Catholic. I fell further from the tree than he did. Anyway, photosynthesis.
So wouldn't the greatest source be the sun then, actually?
Well, that's the energy that drives photosynthesis. But are you suggesting to me, sir, that if I look at some system on the planet Earth, like an ocean or the Earth's atmosphere, that oxygen is being transported to the Earth's atmosphere from the sun, that oxygen molecules are coming from the sun and arriving on planet Earth? Is this what you're telling me? No.
No.
Okay, I do get it. The energy driver, I'm with you there. I'm on board. Roger that. I gotcha. Back to you, good buddy. Okay, that's a source. Now, in the present day Earth, source are biota, dyslexic, so I'll squeeze biota, or the source. Photosynthesis, that's the source there. What's the sink? So when something goes out of the system, we might collectively call those sinks. So present day, in order to have the 21% that we have now at a more or less steady state, where did wind go? How come it's balanced at about, how come it's been about 20-ish% for so long? Where's it going? Where's the oxygen get used?
All the organisms in biota that are breathing it in.
Yeah, biota. Biota. And there's also some geota. Geologic, there's still some geologic sinks. But biota, by and large, are the main ones. This is longer term, but so in and out. Okay, so but before, when the oxygen first started coming out, so here's another way to think of a system is like a bathroom sink. And there's our water level. There's stuff going out and stuff coming in. And there's a really great movie, Lorenzo's Oil. We'll come back to that later, that involves this. But I'm just going to run out of time. So anyway, let me get back to super simple systems point of view. Okay, so got the system coming in and coming out, and we have a rate of mass moving in. So flow is a rate, right? Water flow could be like gallons per minute, liters per minute. It's a rate. Rate has what in the denominator? Time. So for those who haven't had calculus, we could say delta mass per delta T. And if we integrate across all the inputs, then we can get rid of area, but otherwise it would be per unit area. But that's coming in. And then there's delta M over delta T going out. And if you've had calculus, of course, that just becomes dm dt in and dm by dt out. And there was this really bright couple of boys, Isaac and I forget, Newton and Leibniz, and they the Newtonian notation for this is m dot. M dot in, that's mass flux, pretty much. It's dm dt. So this is without calculus. This is just calculus. This is calculus or differential equations. And this is Newton's notation. So m dot in, and then m naught, that's the initial mass at time 0. And then there's m dot out. Write it cleaner here. So that's equivalent to, well, it's identical to dm dt out, and that's nominally equivalent to change in mass over change in time out. Notice that time is a unit here, okay? So from this, we can abstract the simplest of one of our most fundamental governing equations, the mass balance equation, MBE. I can do mass bal equation. Jeez, getting dyslexic here. So mass as a function of time, m of t equals, this will be on the test, initial mass plus what comes in, m dot in is the simplest notation, and guess what, minus m dot out. I'm running out of paper. Rewrite that. M of t equals m naught, that's the initial mass, plus in minus out. Make sense? Cool? Got it? That makes sense? So this here, this flow in, this would be it's a flow, it's a rate, and it's coming in. And whatever the water level is at some time t, that's m naught, and m dot or flow out, that's how fast it's flowing out. Right? Make sense? So we'll have these balance equations for 3 things. We'll have mass balance equation. And what are these others? Anyone want to hazard a guess? This is thermodynamics. That'd be energy balance equation. And the last, charge.
Oh, charge.
Charge balance equation. Okay, so I know we're out of time, but just super briefly, so what happened with our great oxygen event is before we reached, so if this is not changing, if when in equals out, then we have a condition known as steady state. Write that down. Steady state. It's a dynamic condition. A subset of that we'll come back to. This is an open system. Open system. System is open. Stuff comes in and stuff goes out. It's an open system as opposed to a closed system, like we learned in equilibria. Equilibria is a subcategory of steady state where it's reversible. But anyway, okay. So, but before the Earth's atmosphere went up, we had O2 coming into the Earth's atmosphere. And we had, nowadays, we have O2 going out of the Earth's atmosphere, largely due to biotic consumption. But before it built up in the atmosphere, the level was super low. And before it built up, we had this sink. This was geological sink. And this had to be basically filled up. This was the banded iron formations. So this had to be sort of filled up before the levels of oxygen could build up to their current 21-ish%, where we are now nominally at steady state and have been for a long time. But that first bit of oxygen that came out, it killed a lot of things. And then a lot of it got soaked up by the banded iron in a sequential series of events that spanned about a good chunk of 1 billion years. And then finally, at some later time, when a lot of these geologic sinks were satisfied, then it started to really accumulate, and it reached near steady state conditions in the Cambrian explosion. It actually exceeded 20% in the Carboniferous era. But so now it's nominally steady state concentration. See, I guess it would be, this would be a notation. O2 concentration, steady state is around 21 or 20%. That should be volume basis, but we'll come back to that. Anyway, that's enough for one day. But that's your super quick, snappy intro to systems theory. Look it up. Have a look. Okay? Any questions? I could go on all day.
I was going to say, to add, I guess as part of the excursion, one of the Wikipedia resources you shared with us had to do with the Loma-Gundy event.
Right.
But the contrary, at least what happened when the oxygen levels depleted suddenly, had to do with, I think it coincided with black shale deposition. So that was possibly part of the factor for why the oxygen levels went down.
I'll have to have a look at that.
Yeah, it's the Shunga Francevilian event. Yeah.
Cool. I just got one more to really wonk your noggins here. Oops, and then I'll sign off. But just jot this down. But for fun and amazement, the Azola event. It's so I might say on a test, I might ask you to describe the Azola event in terms of a systems point of view. You can wiki that, pup. That's a lot of fun. Okay, but I talk too much. I know too much. I should be silenced.
Will you put that back on the screen really quick?
Oh,
I didn't.
yeah,
Thank you.
Azola.
The Azola.
Azola. I can say this, you know, as if I have some interesting accent. It is Azola event. Yeah. And it might be a cure to our ills right now, but it was a global atmosphere changing thingamajig. Very exciting, very exciting. These things happen. It's amazing. Okay. It's been fun. There's so much more I want to cover, so try to tie together the fundamentals we've been talking about with the top-down things like the Great Oxygen Event. How did things move between the different compartments, air and water? That's Henry's law. We'll come back to that. It got speciated. Oxygen reacted with geologic things and got locked up as iron oxides and stuff. Related rates in and rates out. Biota started to develop that liked oxygen, as Jessica said. It not only tolerated it, but it started to demand it. I hear in Tokyo they have oxygen bars where you can so many yen and put on a little mask, and that was back in the 70s. Well, yeah, I'm that old. And yeah, I don't know. It sounds like fun to me. I would like to get some sushi first, but okay. Over time. But any questions? I'm happy to chat longer. I'm just going to stop the recording now and